Hey, Denell High School, this is Mr. Ayton, and this is 4.1 Energy. We are on a new chapter, and guys, this will actually bring a lot of stuff from our kinematics, from our forces, from our circular motion. It's going to bring a lot of stuff together, so let's get to it. If you think about it, whenever we're dropping a ball from a certain height, what can we use? We can use kinematics, can't we? We can use our constant acceleration equations to find out the velocity when it hits the ground. And the equation we would use is Vf squared equals Vi squared plus 2AD. And of course, this is using the acceleration of gravity, so we can call that G. It's a height of h, so I'm just going to put h in for the displacement. And of course, we drop it at an initial velocity of 0. So if I do my my algebra there, all I have to do is move that square root over to the other side, and it's square root 2gh. And that's the final velocity. And so guys, if I'm just dropping a ball, I can use kinematics, can't I? I can use my constant acceleration equations. But what happens when we have something going down kind of a curvy slope where the acceleration is changing and the velocity is constantly changing, and it's going faster and faster and then slower and slower and all kinds of stuff? What do we use then? We're going to use a thing called energy. And the crazy thing about energy is often the easiest and only way to solve a problem. If you can't solve the problem with forces and you can't solve the problem with constant acceleration, and you don't know where to go, try energy. Energy usually always works. Okay? And energy, the great thing about energy is always conserved. It might look different. It might look like it's the energy of heat or the energy of light or the energy of potential or the energy kinetic, but energy is always conserved. And the units of energy is in joules. And the great thing we can always do is we can write down this great equation right at the beginning: is the sum of our energies at one situation is always equal to the sum of my energies at another situation. And so we basically have two nice and easy equations for energy. The first is for potential gravitational energy. Guys, this only works in terms of the y, because there's that big word gravitational right there. And it is a nice easy equation. The symbol for potential is U, because of course potential starts with the letter U, and it's the potential of gravitational energy, and that's equal to mgh, mass times gravity times height. It's a pretty easy equation, okay? And kinetic energy is equal to 1/2 mv squared, 1/2 mass times velocity squared. I want to show you just a quick simulation of this dude on a roller skating, or sorry, skateboard ramp, and you can see there's no friction here. There's no air resistance. It's just absolutely perfect. And you can see what's happening is this dude is going the exact same height. Energy is totally conserved. And if I pause it at the top, look at the potential energy. It's totally full. Look at the kinetic energy. It's 0. He's not moving. The velocity is 0 up there, but he's at his maximum height. And what happens when he goes all the way down at the bottom? Well, I didn't do good. I'm going to bring it right there. Oh, that didn't work. Let's go all the way down at the bottom. Almost. Look at his kinetic energy. It's almost totally full. His velocity is the fastest. He's the fastest at the lowest point because his potential energy, his height, is the least amount. But look at that ugly yellowish, orange, whatever color that is, bar. The total energy never changes. The total energy never changes. Now, look what happens if I make this height a little bit less, and I put this guy right on, and I start him. There's too much energy, and he dies. So, that actually happens sometimes in real life. Let's take a look at a problem, because that's what you kind of want to see is a problem and what this is going to look like. And I'm going to show you two problems here. I'm going to show you this red problem first, and then I'm going to show you the green problem. The red problem we can take a look at is we have a 20 kilogram mass, okay? And so it has a velocity of 0. And so what can I do is I can start off and say that he has all potential energy. He has all potential gravitational energy. He does have kinetic energy, but the kinetic energy is 0 because it's not moving. There's 0 velocity. So all he really has is his mgh, and that's equal to his total energy. At the bottom, right at the bottom, we can see that we have gravitational potential energy and we have kinetic energy, but because it's a height of 0, we're going to use 0. which means he's all kinetic energy, 1/2 mv squared. And so we can take a look that the sum of all my energy in scenario 1 is equal to the sum of all my energy in scenario 2, which means here I have potential and kinetic. Here I have potential and kinetic. Okay? And this guy has an MGH. We said the kinetic energy at the top here is 0. The potential gravitational energy at the bottom is 0, but it's 1/2 mv squared. And I take a look, and what do I have? I have MGH is equal to 1/2 mv squared. Okay, and of course the left side is the top, the right side is the bottom. The masses cancel out. The mass really doesn't matter here. And I multiply the two, so I have 2gh. I square root, and I have square root 2gh, and that equals my velocity. And when I do that, and I plug in some numbers, I have 2, gravity is 10, my height, total height is 5. 5 times 10 is 50, times 2 is 100. Square root of 100 is 10 meters per second. Now what's interesting is this velocity equals root 2gh is when we're going from full potential to full kinetic. That's the exact same as my kinematics, isn't it? Nothing has changed whatsoever with my kinematics. So that means my kinematics still apply. And that's how we would go from full potential to full kinetic. Now I want to show you what happens when we go from something like this, where we have full potential, to somewhere right here where we have some potential gravitational and we have some kinetic energy. It's moving a velocity right here. Okay? And if you think about it, my height, I always have to do my height. My height here is 1.8 meters. 1.8 meters high. And so if you think about it, let's go to my equation. The sum of all my energies at scenario 1 equals the sum of all my energies at scenario 2. I have MGH plus 1/2 mv squared. And I want to write this every single time. It makes sense because you end up not forgetting anything. Okay? And of course my velocity is 0 at the top, so we can call that 0. I have a mass of 20. I have a gravity of 10. I have a height. My initial height is 5. It's 5 meters. Okay? Now let's go to scenario 2. Right at this point right here, okay, my mass is 20, my gravity is 10, my height is 3.2, okay, plus 1/2, and my mass is 20, and I don't know my velocity. That's what I'm going to try and find. And of course I have 5 times 20, or 5 times 10 is 50. 50 times 20 is 1,000. I have 1,000 joules that I started with. My total energy at the beginning was 1,000 joules. I have 3.2 times 10 times 20, which ends up being 360 joules of energy, which means the kinetic energy right here, the kinetic energy is the leftover energy. The kinetic energy actually equals 640 joules of energy. And kinetic energy, of course, is 1/2 m, mass of 20, v squared. And if I do my mathematics here, my velocity ends up being 8 meters per second squared. And what speed am I going right here is 8 meters per second. Sorry, just 8 meters per second, not squared. And at the bottom, what do we say our velocity was? Our velocity was 10 meters per second. And why? Because we're at a smaller height. We have more kinetic energy and less potential energy. Guys, I hope this helped. Make sure you do that Google Docs quiz, and I will see you in class next week. See ya.